Hello and welcome. In this video, I'll be covering section 10.4, which is over nonlinear systems of equations and inequalities. My goal for you by the end of the video, essentially, will be to be able to solve nonlinear systems of equations and graph nonlinear systems of inequalities. So what exactly are nonlinear systems of equations? Well, they essentially are just a system that has at least one equation that happens to not be linear. So with these situations, our approach is going to be very similar to a linear system of equations where I would have substitution or elimination or potentially just graphing as our ways of solving. So it is possible that we can have no points of intersection. In other words, not every graph would have to cross over another graph. And if that were the case, we would just say it's a no solution or has non-real solutions. Or we could have solutions such as it crosses once or many times. So essentially, what are these solutions? Just like with linear equations or systems of equations, it's just going to be the sets of points that happen to be those points of intersection written as ordered pairs, at least with what we're going to be doing. All right, so let's go ahead and jump into our first example here. I might recommend each time you have things presented in this format, if you end up recognizing the type of equations you have, just sketch a quick little picture and see what would be reasonable, whether the graphs should even cross each other or not. So with this one, hopefully we recognize that the top one is just a circle with a radius of 5, so that would be something where it would essentially be somewhere out here about 5 on each axis. Again, very, very rough sketch. And then the second one, I'm going to go ahead, because elimination doesn't even look like it will be an option, I'm going to go ahead and isolate a letter. Since this is a linear equation, I think getting y by itself makes the most sense, just so I can get it into a y equals mx plus b format. So add the 4y over, then divide by 4, and we can see that y would equal 3/4 times x. So that would be a line that goes through the origin with a positive slope of 3/4, so it would look something kind of like that. So it does look like it definitely meets here in the third and first quadrants. So I'm at least expecting this to have some solutions that are real. Specifically some ordered pairs where either both x and y are positive or both x and y are negative. So just kind of foreshadowing. Hopefully that will end up happening if I do everything correctly. Now, since this is one that more a substitution approach is what makes sense, and we've already got y by itself with that second equation, I'm just going to substitute it in place of the y in the first and start going. So if we go ahead and make that substitution, we now have this expression here. From here, now we want to try and eliminate my parentheses or find ways to combine things. So we got 3/4 x. If I square that, I got 3 turns into 9, 4 turns into 16, and x turns into x squared. We've got a couple options from here. I think the most logical one, though, is to just clear that fraction out just so we can get it out of the way. So if we multiply everything by 16, that should accomplish our goal. So here, if I go ahead and distribute, that will turn into, sorry, I'm trying to change color, 16x squared plus 9x squared equaling 400. So then from here, it looks like I can actually combine these two and turn that into 25x squared equaling 400. And then divide the 25 off. And that gives us now x squared equaling 16. Last step, take the square root. I'd end up with x equaling positive and negative 4. So it looks like I have to come up with two different things. One of them is going to be when x is 4, and another one's going to be when x equals negative 4, and solve for any y's that specifically pair up with those values. So if we go ahead and do that here, I've got my y equals equation right above it. Y should equal 3/4 times each of these numbers. So it looks like I get, for this one, 3, since the 4's would cancel out. So one of my solutions is going to be the point 4, 3. I'll go ahead and box that up here in the top right. And the fact that that is a first quadrant point agrees with our initial sketch as well. And then the second one, I'm going to plug in now negative 4, so it'd be 3/4 times negative 4. But you can probably foreshadow this one was going to come back negative 3, because the negative sign would stay on the 3. And thus I have my final solution set being 4, 3, and negative 4, negative 3. Moving on to example 2, this one, again, just if we recognize the types of functions we have, it's worthwhile at least sketching a graph. I feel like this one will also be one that we should know at least what they are, the top one being a linear equation. So again, I'll just kind of sketch it up here in the top right with x and y intercepts of 5, so that would be something that just comes down the page about 5 up here. It also crosses the x-axis over at positive 5 as well. And then the second one is a parabola that's opening down because of the negative that's in front of it, but has been shifted up only 3 places. So if I think in terms of what would that maybe look like, I'd have a graph like that. So I think there's a high likelihood this one maybe doesn't actually have a solution, but maybe if I drew my parabola a little bit wider, or maybe that line is close enough that it might. So we'll find out when it comes to actually doing our substitutions and that sort of thing and solving. If I end up getting something where maybe imaginary numbers pop up, at that point we can go ahead and commit to this not having a solution. So again, just sketching a graph sometimes can at least get you pointed in the right direction of what to expect. Now here I already have a y by itself in the second equation, so I'm going to go ahead and just take advantage of that and substitute it into the first one. That gives me now my new expression of x plus 3 take away x squared equaling 5. This one seems to be taking the shape, the appearance at least, of a quadratic. So I'm going to go ahead and try and get 0 on one side, but also try and make my x squared a positive term. So I think I actually will just move everything to the right. By adding our x squared here, I'll take away 3 for that one, and then take away x for this last one. So that'll give me a quadratic now officially set equal to 0. Of positive x squared, I'd have a negative x, and then 5 take away 3, that would be a positive 2. So from here we would look to see if we can maybe try factoring. I can't think of anything that will multiply to a positive 2 and add to a negative 1. So at that point factoring doesn't seem to work, so I'll go with quadratic formula just to see what maybe we get. So that would be the opposite of b, so that would be negative 1, so positive 1. Plus or minus the square root of negative 1 squared is 1, minus 4 times 1 times 2, all over 2 times 1. So right now we can already kind of see on the inside we've got 1 take away 8, which this part right here, that's going to come back negative. And anytime I have a square root of a negative, that creates imaginary numbers. So right now our picture and the math are agreeing with one another that this is one of those situations where it doesn't have any real solutions. So we'll just go ahead and write there is no solution for this, meaning there are no points of intersection for these two graphs. All right, on to example 3 now. So for this one, these are not functions that I would expect you to actually know how to do a rough sketch of. So this time I just included a picture of it in the top right that technically you could do on the Inspire calculators that we have, or the blue calculators we have in class. It's a little bit different on the entry with that. I'll definitely could show you if you needed to in class, but as far as just the visual of what these things are, this one happens to be an ellipse and a hyperbola, the second of which we have not covered, so hence why I wouldn't expect us to know how to sketch it. But as you can see from the picture, this appears to have as many as 4 points of intersection where they could cross. So this one also, as you can see with first glance, we could approach this with more of a, I guess, an elimination idea. Or we could continue on with the substitution approach. So I think most of us probably are more comfortable with the substitution approach. So I'll probably do it that way, where we could, instead of having to go all the way to getting y by itself, we could actually just isolate y squared, since there is a y squared in the other equation. So I'm going to go ahead and with the second one just add y squared over, add 1 the other direction. So I end up getting that y squared would be equivalent to 3x squared plus 1. And now that I have that, I can go ahead and substitute it where I see the y squared right here after the 5, and now start getting this process moving in the right direction. So once I get to these substitutions, here we got 3x squared plus 1 going in this spot, being set equal to 39, and now distribute out and start going after parentheses and combining like terms. So let's see what we get here after we expand. Looks like I should be able to combine that, make that 17x squared, take away 5 from both sides, end up getting that would be 34. So then divide the 17 over, x squared would be a 2, and then take a square root, and we get that x would equal plus or minus the square root of 2. So from here now, we'll have to kind of think of what are all the possible pairings. I've got 1 when x equals negative square root of 2, so that I'll have at least one solution with, but looks like if I have y squared equaling 3 times this negative square root of 2 being squared added with 1, I'll end up getting two solutions here as well, because I'm going to have to take a square root of whatever this result is. So this would be y equaling plus or minus the square root of 3 times 2 would be 6 plus 1, so that's going to be a square root of 7. So that gives me off to the side, if I go ahead and write it, I've got technically two answers thus far figured out, that negative square root of 2 would be paired with a positive square root of 7, as well as a negative square root of 7 because of that plus or minus symbol. So that was kind of a 2-for-1 deal. Now if we do the same thing now with the positive version of the square root of 2, so when x equals positive square root of 2, I end up getting y squared equaling 3 times the square root of 2 being squared plus 1. Just like before, we'd have to take a square root, which means I'm going to have two solutions, or two answers. 3 times square root of 2 squared is going to be 3 times 2 again, 6 plus 1 more is 7. So I end up getting 2 more points because this is paired with two different y's. So one of them being positive rad 2 with positive rad 7. Oops. And the last one being positive rad 2 with a negative root 7. So there's my 4 ordered pairs, and again with any of these, I haven't been mentioning it, but we can always go back and double check our solutions just by making sure everything happens to work in all of the equations provided. So if I did back substitute, we could see that this actually is a correct set of points. On to example 4. This one's similar to the last one. It's a couple of equations I wouldn't expect you necessarily to know how to do a rough sketch of, so I've included a little picture of it in the top right. But even if we didn't have the ability to sketch it, we could still go about trying to go about our solution. Here, looking at the picture, you can likely see that there's going to be two solutions for this, so it's kind of my expectation going in. But with this one, it would look like I could probably just do this another time with substitution, either plugging in an x or a y. It doesn't really matter. I'm going to go ahead and just get y by itself, kind of like all the other ones, by dividing this x over. And we end up getting that y would equal 3 over x, and then from there I'm going to go ahead and substitute that in place of the y. So just like we've been doing thus far, I'm going to go ahead and make that substitution now and start simplifying as best as I can to get the ball rolling. So here it looks like I would need to square both the top and the bottom, so I get x squared minus, and this is going to become a 3 times a 9 on top, so I'm going to just call that 27 over x times x on the bottom will make x squared equaling 6. I'm going to go ahead and clear out the fraction by multiplying everything by x squared. I know that 0 is not going to be a solution from our picture, so I'm not too worried about that domain restriction of I can't be 0, but just kind of take note that technically x was not allowed to be 0 because of that division. If I now multiply through, I get x to the 4th minus 27 being equal to 6x squared. So this again is kind of taking a quadratic format. It just happens to not truly be a quadratic because it's a degree of 4 instead of a degree of 2. But if I go ahead and move everything over to one side just so we can do a quadratic approach, the hope is that I'll be able to maybe factor this into a easy pair of numbers here. So this is going to be, instead of x inside here, it's actually going to be x squared when it comes to factoring, because my middle term is an x squared. I know I need to multiply to negative 27 and add to a negative 6, so that would be a negative 9 and a positive 3. So when it comes to solving each of those, only the first one has real solutions. When I do x squared equaling 9 after adding a 9 over, that will give me, when I take a square root, plus or minus 3. The x squared minus 3, this guy actually has no real solution, so I don't, for this problem, really need to worry about. So I've got my two x values that I potentially could have. So off to the side, I'm just going to identify now what the y's that would be, or what the y's would be if I pair them with it. And we'll just use our y equals 3 over x equation that we created at the beginning, which gives me that it would be paired with 1. So I've got one solution here of 3, 1. And then the other one is going to be what happens when I plug in x equaling -3, which will give me 3 divided by -3, which is -1. So my second solution, or second point of intersection for this one, will be at -3, -1, which, if we look at that picture right above, is a reasonable pair of points. So again, hopefully we've gotten the idea of solving these nonlinear systems. Substitution is generally a good approach, where we can go through and solve. Again, if we can sketch a picture, even better. But even if we couldn't sketch a picture, as we saw with the last two examples, we still could approach it with that substitution idea and hopefully come up with reasonable solutions. All right, moving on to the second big picture idea of this lesson, which is solving a nonlinear system of inequalities. So instead of equal signs, now we'll have greater than and less than, and so on and so forth. So notice with this one specifically on the screen, you've got a pair of expressions that have inequalities involved. So individually, if you recall, if I just wanted you to graph a solution set for one of them, you would be taking into account whether we should draw our line as a solid or a dashed, based on whether we see an or equal to or not. So the top one, with it having an or equal to, I know is going to be drawn as a solid line. The second one, on the other hand, without having the or equal to, I know I would draw it with a dashed line. In both cases, I also, for the solution set individually, I would have one of the sides of the graph being shaded to represent its solution set. So here, since it's a system, we're going to look for more where is the overlap of the two. So as we can see here, we just want to kind of look at what type of thing might we be dealing with. We can almost treat it like it's an equal sign to start. So the top one, as you can see, we have an x squared plus a y squared equaling a number that would be squared. So this is really, if we think about it, matching the format of an equation of a circle. It just happens to not actually be an equation. But when it comes to the graphing portion, we can kind of interpret it like it's an equal sign and then worry about the shading after the fact. So what are some things we know about the circle? Well, we do know, since there's no parentheses with the x's and y's, that the center is going to stay at the origin, or 0, 0. And then the radius is going to be the square root of that number that's isolated on the other side, which happens to be 25. So square root of 25 would give us 5. So when it comes to making our graph here, I can go over to our grid, plot our center, and then count out each direction 5. And then just do our best to try and draw a circle that goes through those points nice and easy. Now, already mentioned before that this is going to be a solid line, hence why I drew it solid, but this would be something where now we would want to go back and just see, like, what do we for sure know about the shading for this. So I'm going to go ahead and just pick a point not on that line. I think with circles, the easiest one to choose would be the center itself, and just see if when I plug it into the expression whether I get a true or false statement. So here, if I plug in 0, 0, it'd be 0 plus 0 is less than or equal to 25. And now I just look to see, is that true? Well, is 0 less than or equal to 25? Well, it's not equal to, but it is definitely less than, so that does check out. So I know I'm going to shade inside. And since I can't really do this lightly with a pen or pencil here, I'm going to go ahead and just kind of take note for myself that for sure with relation to the circle, I will be shading on the inside of that graph. Now the second one, if we start looking at what it is, this one happens to be something that I'll end up for sure drawing dashed. Already kind of mentioned that before, but just to remind myself, that's for sure a dashed line when it comes to plotting it. This one looks like it's just a linear expression because I don't have any powers, so I'm going to go ahead and just treat it like an equal sign. Actually, I'll just keep the inequality. Why not? So I would add the 4y over, then divide by 4. So I'd end up with 3/4 x being greater than y. So this is something where I can identify that it has a slope of 3/4 and a y-intercept, or a b value, of 0. So when it comes to graphing this one, I'm going to go ahead and just plot some points there. I'm going to say start at the origin, have a rise of 3, a run of 4. In each direction. And as mentioned before, we're going to draw this as a dashed line to represent its points as close to that as possible, but not including that actual line. Now for this one, I can't really use the origin this time to test, but I can pick any other random point that's not on there. So I think I'm just going to arbitrarily choose 2, 0. Why not? So if I plug in, let's say at 2, 0, let's see what happens with my inequality. I could go back to the original one if I really wanted to. So let's go ahead and do that actually. So it'd be 3 times 2, which turns into 6. But just to show that substitution, take away 4 times 0 is greater than 0. So this is 6 take away 0 is greater than 0. So 6 greater than 0. Is that true? Yes, it is. So that means I'm going to shade the side that contains, or shade the side with, that point. Sorry for the delay here writing. But that then means for my final answer, it's going to be basically everything inside the circle but underneath that line. So that would be this entire region here when it's all said and done. So basically any point that would fall inside that shaded region I just created should be a solution for this system. So we can maybe just pick a couple random points. Looks like 2, -2 would be one. If I plug that into either of these, plug it into the top one, I get 4 plus 4 is 8 is truly less than 25, so that checks out. And then if I plug it into the bottom one, 6 minus a -8 would turn into something for sure greater than 0 as well. So again, that's not necessarily guaranteeing everything, but it's at least supporting my answer in the fact that I chose a random point inside that shaded region and it happened to work with both. On to the last example. So just a second one to go with here. Similar approach, we just need to find a way to make our graphs, determine which side to shade, and look for where the overlap would be in the end. So here it looks like we've got a couple of familiar functions as well. This would be something where I have a quadratic or a parabola. We know it's opening down because of the negative in front of the x squared. And then the +4 has shifted it up 4 places. When it comes to graphing, it does have the or equal to, so it's going to be a solid line. And let's see, we could maybe just pick a random point such as the origin and just test it as well. So let's say something like at 0, 0, what happens? So I'd have 0 is less than or equal to 4 minus 0. Is 0 truly less than or equal to 4? Yes, that checks out. So I'm going to shade the side with the origin included. So with 0, 0. Alright, so let's actually start putting some points on the grid over there, at least get this one graphed. Again, it is a solid line, so we can with confidence know that we can connect all the dots without having to worry about doing dashed lines. If we go ahead and execute the things we said, it's up 4 places for my vertex, and it opens down, so I'm going to go down 1, out 1 each direction, then down 3, out 1 each direction, then down 5, out 1 each direction, just to follow that quadratic pattern, and draw our line passing through all of those points. And as mentioned before, we already know that we're going to shade basically inside of that or underneath it. So I'm going to hold off on that just because I can't really lightly sketch it. So I'll just keep in mind that's the portion that would be shaded for my final answer. The second one, if we go ahead and start identifying some of its key features, this one there's no powers, so this must be linear. I think it might be easy to just like move the x term over and get that this would be y is greater than or equal to a -x plus 2. So at that point we know our slope would be a -1 and our y-intercept or b value would be up at 2. And for this one again it's a solid line. And this one won't go through the origin, so we could also foreshadow what happens when I plug in 0, 0, so at 0, 0, what happens? I'll use the first one, or the first original version. 0 plus 0, is that greater than or equal to 2? Sorry, not 0, but 2. 0 greater than 2? No, that is false. So I shade the opposite side, so shade side opposite, or not including of the origin. So when it comes to graphing this one will be starting up at a y-intercept of 2, having a slope of -1. So I'm just going to plot every point I can fit on this grid. We can kind of see, let's say I had the follow-up question of when do these graphs actually intersect each other. We actually can see graphically what those points would be. It looks like at 2, 0, as well as -1, +3. We said we were going to shade inside of the parabola or below the parabola, but this time it would be, technically we could also call that above the line. So this time the shaded region happens to be this little sliver on the inside of that. So anyway, hopefully this video has been helpful in at least clarifying our approaches for solving these nonlinear systems of equations, as well as graphing these nonlinear systems of inequalities. But if you have questions, by all means, come find me, ask away, and we'll see if we can figure it out together. Anyway, I appreciate you taking the time watching the video. We'll check you later.